Okay, so the question. Okay, so let me just redo it here. So how are Frobenius lifts and how are these related? Okay, so so the theorem is the following. So one direction is that so let R here over ZP unramified completed be a finite extension. And with residue field K, which is FP bar. Okay, so let A over R be an abelian scheme. Okay, so the first thing that I want to say is that if A is quasi-canonical, and I'll explain what this means, this implies A has sufficiently many complex multiplications, and it's going to be defined over a number field. Okay, so 2 is that, so if A is over R has smCM. So I guess we could say A is over R. Okay, we don't need to make such big restrictions on R now. We can say have it be a finite extension is an abelian scheme. And R, say, a finite extension of ZP. Okay, so this can be, so suppose you have an abelian variety that's over a number field with sufficiently many complex multiplications. Then you know by a theorem of Serre-Tate that it has everywhere good reduction, and then you can find a Néron model and then base change this to something like this. Okay, there's going to be there's necessarily going to be needs. There's going to need to be some ramification to do that. Okay, in general. Okay. So if A over R is an abelian scheme and R is a finite extension of ZP, then if A over R, so if A has sufficiently many complex multiplications, this implies that A is a canonical lift, or is a quasi-canonical lift. Okay, and so essentially the definition of quasi-canonical lift is that it lifts a power of the Frobenius. Okay, so we'll give a proof of this in a moment. Okay, so but let's talk about how this works. Okay, so let's just do a little bit of Serre-Tate theory. Okay, so here R is going to be a complete discrete valuation ring with residue field K is equal to R mod M. I think you can relax the assumptions about this being, so this is algebraically closed. Closed characteristic B. Okay. Okay, so then there's a functor. Okay, so then there's this functor. Maybe I should do, again, I should do this on a separate slide. Okay, so Serre-Tate theory. Okay. So in this setup here, R is going to be a complete discrete. Here, K is R mod M. Or you can take this to be Artin. Okay. And so then there's a functor here. So it's a theorem. And I guess does this need to be algebraically closed? Let's suppose that this is algebraically closed for now. I don't think you need this, but I'm just going to do this to be safe. So, so here is deformations of abelian schemes. Here. Okay. So this thing goes to Hom. Maps of ZP modules. And then this is the p-Tate module. It's not the Bar-Tate group. Here to GM hat of R. Okay, so GM hat of R. So this thing here is 1 plus M. Okay, so this is a form. This is the completion, the formal. So in the paper they call it a formal Lie algebra, but this is a formal group. Okay, so this is a formal group law or formal group. And so this is the completion of GM at the identity. And so the map here goes from, so the map takes a lift, okay, and it maps it to Q of A, the Serre-Tate pairing. So this is a lift, and this is the Serre-Tate pairing here. And it's a pairing between so here, this thing here is the p-Tate module. Tate module. Okay, and let me also remember, enforce is that A0 over K is an ordinary abelian variety. Okay, so let me write down some notes about what I need to talk about in the pre-talk. Okay, so that's what we have. And then okay, so this is what we have. And so if okay, so how do we get the Serre-Tate parameters? So if let's say V1, V2, all the way up to VG. So this is a basis of TPA0 of K. And then we have W1, W2. WG is a basis of TPA0 of K. Then the Serre-Tate parameters so these are going to be these QIJs of A. And this is going to be here in Q of A, V of I, WJ here. And this is in G hat, GM hat R. And as before, this, as I said, is 1 plus the maximal ideal. Okay, so these are the Serre-Tate parameters here. Okay, and these determine lifts formal lifts up to isomorphism. Just as an aside, okay, so let me say that. Okay, so let's do this. Okay, so definition, now canonical and quasi-canonical lists. So definition. Okay, so let A be a deformation okay. So we say that so A is canonical if and only if here the Serre-Tate parameters are 1. In particular, we have this thing is equal to 1 for all alpha beta. Oh, well, let's do this. Alpha beta in TPA0 of K cross TPA0 transpose the dual. Okay? A is quasi-canonical if and only if. So there exists some M in the natural numbers such that for all AB in TPA0 of K cross TPA0 transpose of K, we have that QA alpha beta to the M is equal to 1. Okay, so that's what it means to be so this is a lift, right? So deformations of this is a lift. This is a canonical lift. This is a quasi-canonical lift. Okay, and so we'll do the collection of these. So so this will be abbreviated that. So in here we're going to do A is in canonical lifts, and so here we'll do A is in the quasi-canonical lifts. Okay, so there's some basic lemmas about this thing. So lemma. Okay, so one is that if A is a quasi-canonical lift, so then M looks like P to the R for some R. 2 is that, so quasi-canonicality is an isogeny invariant. Quasi-canonicality is an isogeny invariant. 3 is that, so in particular, we're going to have that the endomorphism algebra of A over K, A0 over K, Q, this is going to be isomorphic to the endomorphism algebra of A over R, Q. In general, you always have that the general endomorphisms inject into the endomorphisms of the special fiber, okay? And then 4, we have that A, okay. And in this case, so let's do some notation. So A is A0 tilde is the canonical lift. Okay, so A is the canonical lift if and only if A has a lift of the P Frobenius. Okay. And, okay, 5. So A is quasi-canonical if and only if A has a lift of the power of the Frobenius, the Q Frobenius, where Q is equal to P to the R. Okay, so these things are equivalent. So there's a way to classify these, and the proof of these sort of facts goes through the properties of the lifting lemma. Okay, so this is found in cats, but you kind of, to prove it, you have to go back to actually put the details together. You need to go back to Messing's thesis. Okay, so this is Serre and Tate. So there's the all important lifting lemma. So to prove these, so we use the lifting lemma. Okay, so what's the lifting lemma say? So the lifting says that if A0 and B0, so this is the lifting lemma. Okay, so what we'll do is we're going to do the setup. So let A0 and B0 be ordinary abelian varieties. Over K with lifts, with formal lifts, or lifts with formal lifts. A and B. Okay, so these are formal schemes. So they're built by limits of things over Artin rings. Okay. And so we're going to let F0 from A to B, A0 to B0, be a morphism. A morphism of abelian varieties. Okay, and so the lifting lemma says that F0 lifts to F from A to B. If and only if, so for all alpha beta in TP so let's do this alpha beta in TP A0 K cross TP B0 of K. So we have so QA of F0. So let's do this. QA of alpha so this thing, oh, so I guess this is symmetric, right? So QA alpha of F0 transpose of beta is equal to Q beta QB of F0 of alpha beta. Okay? So, in particular, that these two pairings are equal. All right. And so, so this is, so the procedure for this, so let's look at a very trivial example. And they're all not so hard, right? So quasi-canonicality, right? So if A is quasi-canonical, or let's say A is, so let's do it like this. If A is A0 tilde, right, the canonical left, then end A0 over K is equal to end A over R because, well, we'll always have QA of alpha F0 transpose beta is equal to, well, this is equal to 1, which is equal to QA of F0 of A beta. Okay, so it's always just going to be one trivially. So this shows you that every endomorphism lifts. And then the converse, just as a remark, in general, we always have so if A over R is flat, then so then we always have end A over R injects into end A0 over K because of what happens to the kernel. So if you look at an isogeny, right, then or an endomorphism, and you look at what would happen to the kernel, right, you should be able to convince yourself that that this is the case. So like you get if this isn't the case, right? Suppose there's a kernel, right? So suppose something maps to 0, then you'll have some sort of kernel of an isogeny or an endomorphism. Let's say it's an isogeny. There's a kernel of an isogeny, and it has the property that that its special fiber is going to be massive, right? And so you don't have things like that. In particular, I think your base changing. Let me think about that. Yeah, you're base changing a flat map, so it has to be flat. right? So you're base changing by the identity map, and that needs to be flat, and so you need something that's flat. And then if you have something that's just blows up in dimension, it can't be flat. Okay. All right. Okay, so now we can prove the theorem. All right, so the theorem here. So the proof that QCL are the same. Okay, in the simple case. Here we go. All right. So we're going to show that quasi-canonical implies sufficiently many complex multiplications. So the setup here again, A is A is over R. So let's do it like this. Okay, so so if A is QCL, quasi-canonical, this implies that A is isogenous to the canonical lift. Okay, so this implies that A and A over R, Q, is going to be isomorphic to and A tilde over K, right? And then this thing is Q adjoint pi. Okay, so this is by the ordinarity. Okay, so by the ordinarity hypothesis. So, okay. All right, and so this means that, so since we're doing this rationally, okay, so here pi is the Frobenius, the p Frobenius. Okay, so this tells us that there exists some m such that sorry. So this is the easy part, right? So this already proves that, so now we have some j from F, which is Q adjoint pi. This is a CM field, right, into the rational, and then the degree of and then we have Q pi over Q is 2g. So this implies that it has sufficiently many complex multiplications. This is the easy direction. Okay, so then so the other direction, right, is the following. Okay, so the characterization of lifts. So the characterization of being quasi-canonical is having a lift to the power of the Frobenius, right? So SM. So let's do the other proof. Okay, so in this case, we're going to take R finite over a finite extension, possibly ramified. Okay, and then we're going to take J. So by hypothesis, we're supposing that J here, from F into the endomorphism ring of A over R, Q is a complex multiplication. Okay, and so we're supposing that it's smCM. I.e., F over, so this is injective, and F over Q is 2G. Okay, so that's a CM field. Okay, so we know that from general principles, so we know that the endomorphism algebra so this thing here, so the center of this is Z adjoin the Frobenius, the Q Frobenius, where Q is the cardinality of the. So let's say that possibly ramified. Let's say the residue field is K, without loss of generality, right? Okay, so where Q is the cardinality, okay, where Q is the cardinality of K. Okay, so there is a general theorem. There's this, from the Serre-Tate paper, so this is a 1968 Serre-Tate paper. There's an argument that says that that shows that the reduction of here. So if I take J of F and I intersect it with the endomorphism ring of A over R, and here in the endomorphism, so we're taking the intersection inside the endomorphism algebra, is its own, so let's say it is inside the endomorphism algebra of the abelian variety over the finite field, generates, let's do this, let's say is its own centralizer. So in particular, it contains the center. So the reduction of JF intersect this thing contains the center. The center. And this is equal to Z with the Q Frobenius. Okay, so in particular, there is some pi of A in here, right, that maps to this. So this tells us exists a lift. Okay. All right, and that's all I really have to say.